Today we're talking about a decentralized world database, the Bluzelle database, and I am Neeraj Murarka, CTO of Bluzelle Networks. Quick little slide here about who I am. On the left you can see a picture of myself running as a libertarian in British Columbia, Canada, where I'm based out of. And on the right is an interesting slide showing myself having met one of my real heroes, actually, in the world. That's none other than Linus Torvalds. I bumped into him at a Costco warehouse in Portland, Oregon, several years ago. So it was a real pleasure to meet him, and shows some really important moments in my life. So quick little history about Bluzelle for those of you in the webinar that aren't familiar with us. We were a tech pioneer with the World Economic Forum and part of the Global FinTech 100. We've built KYC shared ledger with a consortium of banks including HSBC, OCBC, and MUFG. We've also built insurance platforms and mobile personal injury products for a global insurer. Some of our payment systems were actually put into a POC with Temenos, which is a core banking system used across the world. Some of our partners include KPMG, Microsoft, as I said, mentioned Temenos. We work with Ripple, Ethereum, and we've got a partnership with British Telecom. So let's get right into it. What is a database? Well, really simply, a database is really just a structured set of data held on a computer. It doesn't really encompass anything with respect to being able to store other types of data or management of the data itself. So typically when we talk about a database, we're actually talking about something else called a database management system, which I'm going to get into. A data store is a repository for storing many different types of things, not just structured data, but other simple types of data like files, emails, etc. And then we get into database management systems, which are the entire systems that allow you to interact with the data. So it allows you to capture data, analyze the data, back it up, restore it, do all the creation, querying, updating, administration of the database itself. So, largely for the sake of this presentation, I'm going to refer to database as the term database, but in fact, we're usually talking about a database management system. And in fact, I want you to keep in mind the term key value store, because that's a special type of database that we're going to be using. So, Bluzelle is a NoSQL, or not only SQL, database that does key value stores. Some examples of other types of databases similar to this are eventually consistent ones like Dynamo, ordered ones like Berkeley, in-memory databases like Redis, or on-disk ones such as LevelDB or RocksDB. So key value stores, quite simply, it's like a dictionary. So if you've used any modern programming language, you have a dictionary or a hash, and you have a key, and it points to a value, and you can consider it an associative array that you can store and retrieve data from. So what is decentralization? Well, let's talk about what centralization is first. So centralized systems are actually what are the most widespread model right now for software applications. If you're using the cloud, you're typically using a centralized system. It's powered by open source software, typically. Things like Linux operating system, Apache, the entire Free Software Foundation GNU stack. But the interesting thing is a lot of that software that you're using is not actually open source for you to use yourself. The licensing of the software is actually only applicable within the server environment. It doesn't apply to you. You have distributed environments where the computation could be spread across multiple nodes, but again, it's not a decentralized model. So now if you go into decentralization, you're talking about a different mode where, you're dealing with situations where even if there's node failures, your system keeps going because there's really no center, there's no core, there's nothing really that's going to go down or bring the entire network. And this kind of really segues into what we're talking about in our presentation here, which is trustless computing, and that's really the most important thing. People talk a lot about blockchain, and what they don't realize is blockchain is really a part of a larger family of technologies, which I like to refer to more often, and that's trustless computing, where you now have concepts like consensus and attack tolerance that come in so that you can basically bring in arbitrary machines and be able to capture the resources to provide services that were previously only possible with centralized or distributed systems. So let's now talk about our decentralized world database. Give me one moment here. So what is the Bluzelle promise? Well, we're building a database that's going to be powered by free and open source software. So just jump ahead a bit. Our database, think of it as a key value store plus the network. It's all going to be under the AGPL v3 license. Real briefly, the AGPL v3 license is very similar to the GPL license that we're quite familiar with. One of the key differences here is the GPL license doesn't specifically provide any protection or rights to people who are using software that is licensed under the GPL in a network environment. So for example, if you're connecting to a server that's running Apache, running on Linux, and let's just say that server and the operating system on that machine was powered by a GPL, you wouldn't be entitled as a person connecting via the web to the software on that machine as per GPL. Now with AGPL, you will. That means that if you're using software as a service, for example, and that software gets forked and it's modified, you will be able to take advantage of that software as well as having access to the code. So Bluzelle, we really envision a decentralized web where not only is your database decentralized, but the entire stack is decentralized, whether it's file services, CPU services, domain name server services, and of course database services. The Bluzelle project that we're talking about here, it actually contains many different aspects, including the daemon, which is something I'm going to get into, APIs, and libraries. The libraries are actually connectors that allow developers to be able to talk to our database and use the database services, which are fundamentally create, read, update, delete, or CRUD, as well as the tools necessary to interact with the database. The Bluzelle on the blockchain is going to exhibit several benefits that you don't typically see with a centralized environment. Some of these include security, reliability, and scalability. So, in a nutshell, I'm going to actually get to the next slide, and we'll talk about that. We're a unique combination of the decentralized token economy with open source and trustless computing that embody many of the same philosophies. So let's just take a quick look at the past, present, and future. The past, you had a single system model on the left. Single system, and that means that if anything went wrong in the entire stack, anywhere in the system, your database was done. Present model, it's a cloud-based model. It's better, but there's a load balancer, and ultimately if somebody gets access to your load balancer or gets into one of your zones, they have access to almost all your data, or typically all of it, and they can corrupt your data, steal your data. We've seen several examples that have happened in recent times. The future model, which is on the right, is the swarming model where your application actually connects to these swarms. Each of these units is actually a swarm, and within it are nodes. And that's I'm actually going to jump over to another slide. Just give me a moment here so you can see that particular visualization. So over here, you can see the MetaSwarm, and this is basically the Bluzelle database. You can see all the different swarms, and each swarm is actually encompassing the entire planet. The point of a swarm is to have no geographical isolation, so that if something were to go wrong in a part of the world, let's just say all the networks in Canada went down, your swarm would still work because there would be several nodes in each swarm that would be outside of Canada that would still be functioning. So the key idea here is your data, which, let's see here, your data here, which is actually chopped up into partitions, gets stored into each of these swarms. And by being stored in each of these swarms, you have redundancy because there's many nodes in each swarm. Each of these orange circles is a node. And then you got the leader node, which is the gray one. And when you pull your data, it actually gets pulled in parallel across all the swarms. Now I'm going to take a look and see if we have any questions. Give me a moment here. I'm being asked by David, do you have any info support for a query API for encrypted data? Okay, so if I understand it correctly, basically the question is, do we have support for encrypted data? The answer to that is it's on the roadmap. We will be supporting encrypted data in the future releases. The initial version of Bluzelle is going to be requiring that developers encrypt their data in the application there. So yes, we will have native support where you can encrypt your data by having public key cryptography, but that's a future feature. One of the aspects we want to be able to have is to enable developers to do searches on their query data, and that's an advanced feature. So we won't be supporting that at the present time. So yes, it is coming in the roadmap. Let's see. So let's move on. Are there any other questions? Doesn't look like it. All right. So going back to our previous slide, just switch over to it. All right. Great. Oh. All right. So the current weak model that we've been talking about, the centralized model, you've seen leaks like Equifax. Uber had a leak where a lot of customer data was available. And then, of course, you've had a situation of ownership where Facebook, they're facing problems right now where Cambridge Analytica was able to leak the information for tens of millions of users. And it's really brought up a real issue of ownership of data. And of course, we have GDPR coming down from the European Union in May. And it ultimately makes you ask this question, wouldn't it be nice if you controlled access to your own data? All right. So the decentralized ecosystem stack, this is how we visualize it. So what we have on the left is the decentralized stack, and on the right, the current stack, the centralized stack. So I'm going to talk about applications, operating systems, file storage, and then data storage and management. So on the right side as an application, a lot of us are using Facebook Messenger, WhatsApp. The decentralized version of that you might consider to be Status. So Status was a decentralized instant messenger that came out last year. They had an ICO, it was very successful, and that's their decentralized analog. Now on the operating system, a lot of us use Linux or Mac or even Windows. Operating system that you might want to look at on the decentralized, you can consider it Ethereum. Ethereum is kind of a world computer, and you can run Turing-complete applications on it. Now, file storage in the centralized world, you got things like AWS S3 or Azure. On the decentralized mode, you got things like Filecoin or SIA or storage. Now, on the data storage and management side, in the centralized world, we have things like Oracle, MySQL, MongoDB. That's where we come in, Bluzelle. We're that decentralized database that's really necessary to complete the decentralized ecosystems stack for software. So, the early adopters that we're looking at are DApp developers that are typically going to be building applications on Ethereum or on Neo or on Zilliqa or on other blockchains, and they're going to need this entire stack, and the database is a critical part of software development, as most developers will know. So what is Bluzelle in a nutshell? Well, we use your idle computer hardware by incentivizing people to rent out their resources to create a decentralized crypto-economic database network. That's the best summary of our database. Now, some of the technology highlights of our database include swarming, 2D partitioning, and consensus. Swarming is the slide that I talked about earlier, where we showed all the different swarms that are in place. And then when we go to 2D partitioning, that's where I was showing you the partitioning of the data into different shards or partitions that get stored out to each swarm. And consensus is actually really important, because consensus allows an arbitrary set of nodes in a trustless network, such as the Bluzelle network or even a blockchain, to be able to come to an agreement on the status of the network. Now, typically, if you have a centralized model, there's a centralized authority that makes those decisions, but that in itself is a weakness. So with consensus, you need to have an algorithm where a bunch of nodes, none of which has any special permissions, can decide what is the state of the network. So in our database, each swarm has to be able to determine what is the state of each value that's being stored in that swarm. I'm going to go over a quick little interesting example in the future of something that could happen where let's say you're playing FIFA on your PlayStation 4, which has 1 terabyte of storage, and you're managing your leagues or playing your games or whatever. So now, imagine if your PlayStation 4s, each of them were actually storing the data. So let's kind of back up here and talk a little bit about producer and consumer. So what is the Bluzelle network really? It's a producer-consumer model, for those of you who haven't been watching our previous videos, where producers provide their hardware and they're storing data from consumers on their hardware. So each of these PlayStation 4s in this hypothetical model could be storing the data, and the consumers themselves are the consoles. So you could be your FIFA game could be storing its data within this network, and the Bluzelle token is actually what's driving this crypto economy. So you use the Bluzelle token to pay for storage, and then the actual producers who are running the node software on each of their machines are earning those tokens. Let's take a quick look and see if there's any new questions. All right. Let's see here. Another question from David. That means that at the moment you will only support key value query, correct? Yes. Another question is about performance and scalability. How do you compare, for instance, with Cosmos DB that has great performance and scalability? I'm asking this because I'm trying to understand how will you sync the data that is spread into multiple swarms and taking performance into account. So that's a great question. I'm not really going to comment on how it compares to Cosmos DB because I don't have the metrics in front of me, but I can say that the two real analogs that we like to use when we're comparing our database is torrents and CDNs. The reason we use CDN, the CDN metaphor or comparison, is imagine that you're pulling in your picture from Facebook. Typically, you're going to not pull it from a server that's on the other side of the planet, but you're going to pull it from the node that's closest to you. That's what a CDN, part of what it does. So with Bluzelle, you're actually not pulling your data in from just any node on those swarms that are spread across the world. You're pulling it from the nodes that are closest to you that make the most sense to pull it from. So from the standpoint of latency, you're going to get the highest speed possible. Now, in terms of the performance and parallelism, if you're pulling in data across multiple swarms, which is pretty likely, you're pulling in 100 rows of data, it's quite unlikely they're all going to be in the same swarm. They're probably going to be spread across multiple swarms. But again, like a torrent, you're going to be pulling in those rows from each of those swarms in parallel. It's not in series, it's in parallel. And we've actually done tests. It's quite fast. I mean, obviously, if you're in a situation where you're building an application that requires LAN-based speed in a machine, on the same network as you, that's a different matter. But the speed is actually quite fast. Okay, so we're going to switch back and continue through our slide presentation, and then I will get to do some demos for you. So, why go open source? Well, quick things here, because we're not just talking about the product here, we're also talking about open source. So we like the speed of innovation. It kind of segues into the fact that no one is really smarter than everyone. We want as many people in the community to be engaged. So, part of that's going to be our bounty program, our hackathons, but at the end of the day, we want everyone to be able to contribute to our software, and that's part of the reason it is AGPL v3. We're here to build an infrastructure for the decentralized internet that benefits all, and it's really in line with the open source philosophy. And as I said, there's economics to go around bounties. So we're going to be putting out bounties at hackathons, but also to the public where they can put in open source contributions and we'll be rewarding them. We recognize the fact that, even though it is open source, contributors definitely love to have those sorts of rewards. So some of the things we're going to be working on improving is a mailing list, a Jira bug tracker that's actually open up to the public and not just private, the GitHub wiki. We're going to be doing presentations and webinars such as this one, focusing on APIs and libraries and tools, more documentation, including a branching strategy. And one of the nice things is we're also going to be implementing regular virtual office hours for developers. And we're planning to have 2 a week that are going to be aligned with different time zones of the world to provide the best convenience to people. Let's go back to questions. Okay, we'll continue here for a moment. Who is the who's our developer today? Yeah, so we have our source code already on GitHub. As you can see, there's a URL there, and you can actually grab the code, you can build it, and you can run your own mini swarm. At the end of April of this month, we're going to be putting out a version of our database that's actually going to be used in our hackathon in Vancouver, Canada, and that'll be a mini swarm that you can actually run on your own if you wish. You'll be able to propagate the values and deltas handed down by the leader by the consensus state machine, which we're actually built in, which is called Raft. We're actually using a modified version of Raft. All right, so at the end of June, we'll be actually releasing the full version of Lovelace, which is our our single swarm version of Bluzelle. It'll allow you to create, read, update, and delete of key value pairs on a single swarm. And we will also have libraries on JavaScript to be able to do that, as well as connecting with WebSockets. And we will also have read-only support from Solidity and from Neo. As I mentioned here, there's you should go to the Bluzelle blog website listed here if you want to get updates. A quick use case, 0x is one of our partnerships, and as you can see here, the pain point with 0x is relayers. So the relayers need to be able to store order book data. So what they can do is actually talk to an API abstraction layer, which can be written in C++, C#, C, or Python, and then talk to the Bluzelle MetaSwarm. So I'm not going to go into too much detail about this use case, but the key idea here is you can make the reads through this layer, and then callbacks come back and can provide the data to the relayer. We're doing the read flow in this particular slide, but there's also similar analogs you can draw for doing writes. Now let's go back to questions. David has another question. So I see that he's asking about the cap theorem and where we're at. David, can you possibly expand upon that? And I sort of see where you're going with this, but if you can ask a more specific question, that would be great. In the meantime, I will continue on to my next slide. And actually, you know what? I'm going to move on to the demo. So give me a moment here so I can switch windows. Let's see here. All right, so okay. So what we're going to do here now is we're going to run a simulation of a single swarm, so you can just see the life cycle of what a swarm is doing. Let me turn on also the actual visualization itself. All right. There we go. There's that. And now you can see, right, clicking on the wrong window. Here we go. So we're going to connect to that simulation, and here you are. So this particular screen is just showing the messaging and timestamps and the timers for each of the nodes. But the really interesting here is the node graph. So what I'm going to do is I'm going to make this a little bigger. Hopefully it doesn't mess up the stream. It did, obviously, so let me make it smaller again. All right. There we go. So right now we can see there's 10 nodes in our swarm approximately. And there's a life cycle going on. You can see that there's green nodes, there's red nodes, and there's blue nodes. Let's see here. And the red nodes are actually nodes that have just died. We're just basically showing a demonstration of the life cycle where nodes can come to life, as in if you turn your machine on and join the swarm. Red nodes are nodes that might have been powered off, they were shut down, they died, whatever. And then the blue nodes are the ones that just came to life. So we can see the point of this is that the swarm still persists all the data. It doesn't matter if some nodes go down or some go up, the node itself will remain. And you got a green node with a star, and that's actually the leader of the entire swarm. So what I'm going to actually do now is I'm going to change the number of nodes in the swarm from 10 to 40, just for fun. And then we'll switch back to the node graph. And you should see in a moment that the number of nodes is actually going to jump quite a bit. And it just makes it a more interesting visualization. So one of the principles we're going to be doing with our swarms is determining the maximum number of nodes to put into a swarm and a minimum. The minimum being the minimum number of nodes required to have redundancy so that, even in a catastrophic situation where a whole bunch of nodes go down, the swarm has enough nodes alive so that your data is kept safe. So we wanted to make it statistically impossible for your data to be lost. At the same time, we don't want to have too many nodes in the swarm. It's a waste of resources. So ultimately, if you have a swarm that is saturated or has enough nodes, we would create a new swarm. So whenever you join the network actually determines which swarm you get put into, and at some point when all the swarms are saturated, a new swarm can be created. All right, let's go back to questions. Okay. Yeah, so in terms of data consistency, the question is making parallel reads and writes. So in the long term, what we are going to have is consistent nodes and nodes that are not consistent. So I'm not sure if this is necessarily answering the CAP specific question, but if you connect to a swarm and you're asking for data, what you'll be able to do in the future is you'll be able to actually, depending on how much you're willing to pay for the read, you can determine whether you want to do a consistent read from one of the nodes that would be guaranteed to have the most latest data. So let's just say, for example, that in parallel you're doing reads and writes. So you write the value a equals 1 to a swarm. Now the question is, if you do a read from the same swarm around the same time the write happens, what is going to happen? Well, if you do the read, the low-cost read, so to speak, you will, thank you, David, saying you are answering the question. So if you do the read at the same time, for a low-cost read, there's a potential where you might read the old value. So if the value of A was 2 and now you set it to 1, you may get the old value, and that's fine because in certain cases, such as let's say a Facebook wall where somebody updated the wall, it's not really critical to get the latest values of the data. Now on the other hand, let's just say you were storing banking information on the Bluzelle database, and where you were doing a read, you would want to have a consistent read. If somebody went in and changed the balance of an account from say $100 to 0, you would want to make sure that if you're reading that value, you're actually getting the new balance. We can imagine what would be the consequences of not doing that. So in that case, you would not do a low-cost read. You would do a more expensive read, and that would require more Bluzelle token cost, and you would get the data consistency. And of course, there may be a delay if you're doing this just because you have to hit specific nodes that are considered the consistent nodes, and they're guaranteed to have that property. Okay. So let's get back to this, and what I'm going to show next is going to be the text slides, which I went over earlier. So just give me a moment. All right, there we go. So let's pull that up. Right, so this slide. Okay, so we already went over this slide, and we're talking about key value pairs and horizontal partitioning, and we all understand that you have a set of data, and these are all the key value pairs, and ultimately when you put it into the Bluzelle database, it will be chopped up into pieces, and each of these partitions will go to each of to different swarms on this slide. Now, I'm going to show this real quick, and then we'll move on because this is not something that's necessarily going to apply right away. But eventually, if we have a high enough number of swarms, we may end up with a situation where we need a distributed hash table. And this is the Cadelia hash table. And ultimately, it just talks about the fact that every swarm doesn't need to know about every other swarm. So, you might have swarm Bravo over here on the left side that needs to know about swarm Fox. It doesn't need to necessarily have the address of swarm Fox or IP address or whatever means to reach swarm Fox. It can actually use a Cadelia process, hash table lookup, and in logarithmic time be able to find any other swarm on the network, and as a consequence of that also be able to find any other node. And that's just what we're talking about here. We won't go into too much detail about this. Let's pop over and see if there's any questions. Okay, great. Looks like David got the answer to this question. Super. I'm only getting questions from David, so if anybody else is tuned in, please ask questions. Now, we're talking here about the Raft state machine, some details about Raft. We are using Raft, but we have actually modified it. One of the attributes of Raft is you do have a leader and you have followers. And we don't want a situation actually where leaders go down often because it does have an impact on performance. So one of the things we've changed with Raft is we're changing how the leaders are chosen. Not just anyone can run as a leader. So typically in Raft, there's a timeout that all the nodes have, and if they don't hear from a leader within that timeout, which is a random timeout, the first follower to actually have that timeout will run as a leader. So it's a model where anybody can run for leader. So in our model, we actually discriminate, and nodes that are wanting to run for candidate, they can only do so if they meet certain criteria. So we have things like karma, uptime, many different things. But the key point is to minimize the chances that a leader is going to go down by choosing better followers to run for leader. The right side part of this slide talks about the process of updating a value in the log. So basically what you're doing with Raft is you're really just keeping this log at the bottom consistent. So you got a value of a equals 6, that was a write, then b equals 10, another write, then n equals 7, which was another write, and then you had an update, n equals 9. So it's really important that all the nodes have consistent values or else you have a problem. So this is the Raft consensus state machine that we're showing here. Let's see if we have any questions. Nope, none right now. All right, let's move over to this one. Pretty quick slide. Just talking about the fact that on Ethereum we have our ERC20 token, which was part of our token sale in January of this year. And then we have a gateway smart contract that allows you to convert one-to-one from the Bluzelle token on Ethereum to the BNT token on Bluzelle's own network. So the Bluzelle native token, or BNT, is the token that will actually run within the Swarms network that we have. And it allows you to have the high-speed microtransactions that are necessary to do database transactions. As we probably know, on Ethereum, the cost of doing transactions is quite high, and confirmation times are non-deterministic and rather long. Obviously not applicable for a database environment. Okay. I believe, let's see if we have any more questions here. I'm going to open up this slide now because there's one more slide I wanted to talk about. And, well, questions and answers are open at all times, so please feel free. Join the conversation. So we have here 6 different means to be connected to the Bluzelle community. We have Slack at bluzelle.com/Slack. We have our email list, which you should join. There's Twitter. As I mentioned, GitHub for all the developers. You should definitely get onto that GitHub and clone our repository and try it running a swarm. We have Telegram, and then we're also on Medium, where you can definitely see all our posts. And let's see here. I believe that's it. I'm going to give a few minutes for any more questions. I guess in parallel, what I can talk about is some of the questions that have come up, and I'll give the public some time to ask questions if they have any. So one of the questions that comes up often is, how do we ensure that someone who's acting as a producer, so I can elaborate a bit on this, a producer is running our daemon software and they're earning tokens for storing data. But the question then comes up is, what if somebody's trying to cheat? What if they're acting like they're storing data, but they're not really storing the data? They're just dropping the data once they receive it, and they're earning the tokens. How do we prevent that? So we actually have a proof of storage challenge that can happen, and it's random. So let's just say you're a node and you act that you stored certain data, a equals 5, for example. Now, if you drop that data, there's a possibility, whether you drop it or not, that you will be challenged at some point afterwards, being asked, prove that you have that data. And if you're not able to respond to that positively, you'll be assessed an economic penalty. So what is that economic penalty? Well, in order to actually join the network as a producer and run a daemon and become one of the nodes that are storing data and earning tokens, you actually have to put up a stake. So you have to put up a stake of Bluzelle tokens ahead of time, and that stake is kind of like a deposit. So if you're breaking the rules, cheating, if you fail the proof of storage challenges, you can lose some or all of that stake. Another thing is the karma. Your karma is kind of a score of the health or your reflection of past behavior of your nodes, and your karma could be reflected upon by multiple nodes. And if you cheat the system, or you're just not running a node that is reliable or up all the time, your karma can be affected. So it can be affected by many ways, by many things, and that has a major economic impact on what you're going to earn as part of the Bluzelle network. I don't see any more questions. So I believe I will conclude our webinar for today. I will just check and see if there's any other questions on our YouTube channel. And if not, I will say thank you very much to our audience and look forward to having you join our next webinar. You can check out the dates for our webinars and our blog, basically